Welcome back. So we continue the discussion on this issues on the design. Now, what we'll talk about um, blade shape optimization. So blade shape optimization, or rather blade shape. I mean, this is for one can think about optimum rotor with weak rotation. Okay. So essentially what we'll talk that the blade shape for an ideal rotor, which includes the effect of weak rotation that we can determine using the analysis that can be developed for general rotor. Now the optimization actually includes weak rotation but ignores. So essentially the optimization that includes weak rotation but ignores CD, which is essentially considered to be zero. That means the drag and tip loss for which the F factor would be 1. Now, what one can do, how this uh, blade shape can be determined for optimum rotor with weak rotation. So here the procedure that we'll discuss by considering the weak rotation, but at the same time you consider there is no tip loss, there is no drag. So you can find out the optimum one by taking the partial derivative of the part of the integral of the CP, which is the power coefficient. Essentially, the CP is function of angle of relative wind, phi, flow angle, and other things. We can now find out that system by taking this derivative or so. So what can do del phi of sine square phi cos phi minus lambda r sine phi plus lambda r cos phi, which is 0. So this yields that lambda r equals to sine phi 2 cos phi minus 1 divided by 1 minus cos phi 2 cos phi plus 1. This is what you get. So some more, if you do you're doing some more algebra, what we have P, we get 2/3 tan inverse 1 by lambda r, and we get quad is 8 pi r BCL 1 minus cos phi. Okay, so that is what you get. And also we can calculate A from equation 30. Okay, and other relevant equation, so which is 1 divided by 1 plus 4 sine square phi sigma prime CL cos phi. So that's what you get, and you get A prime equals to 1 minus 3A, 4A minus 1. So these results one can compare with the results for an ideal blade without wake rotation. So which you get from essentially from equation 20 and 21, you have Phi equals to tan inverse 2 by 3 by lambda r, and C equals to 8 pi r by BCL sin phi by 3 lambda r. Now, one has to note that the optimum values for the optimum values for Phi and C, including with rotation, are often similar to, but could be significantly different from those obtained without assuming wake rotation. So this optimum value, including wake rotation, can be significantly different from values without wake rotation, which is quite obvious because the wake rotation takes into account a lot of physical processes that usually takes place in realistic scenario. Also, as before we have done, we can select alpha where CD by CL is minimum. Now, solidity is again is the ratio of that planform area of the blades to the swept area. So what we get, the solidity sigma 1 by pi r square r is to r CADR. Now, again, one can find out the optimum blade rotor solidity. And when the blade is modeled at set of in blade section of equal span, so let the blade is modeled as in blade sections of equal span, then we can have solidity defined at B by N pi summation of I equals to 1 Ci by R. So that's how you can also find out the optimum blade rotor solidity. Okay. Now, blade shapes or sample optimum, for different conditions could be obtained. Assuming different lambda value, different B values. So that includes the wake rotation and in obviously, but so that's how you can use these parameters to find out those things. But one has to kind of consider that that would show different kind of variation. One of the variation that one can have that the slow, any particular slow 12 bladed, for example, machine would have blades that had a roughly constant chord over outer half of the blade and smaller chords closer to the half. The blades can have significant twist Also, faster machines would have blades with increasing chord as one wind from the tip to hub. Blade twist have could be significant for different things. So essentially, one can use this to find out the optimum blade shape and mm, uh, for that. Now, what we'll talk about now, we can talk about in general some rotor design procedure, which is in general way we will talk about that. So the blade optimum or the other factors that we have talked so far, those can be used in generalized this rotor design procedure. Um, this procedure begins with the choice of various rotor parameters and the choice of airfoil. So obviously, this includes the choice of airfoil and other uh, associated parameters. Okay, so obviously one can assume or one can kind of determine the initial blade shape by assuming weak rotation, considering weak rotation, and then the final blade shape and performance can be determined iteratively, considering so initial design or shape can be considered by including weak rotation, and then the final shape can be determined by considering drag, tip loss, other manufacturing factors, etc. So that means what you can do, the uh, analysis that we have so far uh, discussed upon or talked about. So the idea here is that you start with some initial shape or the blade, and that you determine by considering the equations that we have obtained. But obviously, you consider the weak rotation. And then when you move on to really optimize the thing, then the final shape you can optimize or design by iteratively. Obviously, that time you consider all your drag loss, tip loss, other manufacturing constant, so that the how much twist or the chord at different sections could be allowed to have proper tolerance and all this. So there are two-stage procedure. You have some initial design, and then you consider each of these issues in practice that you encounter, and then go to the final step. So the first stage could be, let's say, the uh, determination of basic rotor parameters. So that would be the first test to do. I mean, once you get the basic parameters, and then you can uh, find out the final parameters through iteration. To begin with, one can decide what is the power that is needed at a particular wind velocity u. So one can include the effect of probable CP and efficiencies eta for components like gearbox, generator, pump, etc. So then we can have P is CP eta half of rho pi r square UQ. That's so that means you are considering some power coefficient. You are considering some efficiencies of this mechanical component like gearbox, generator, pumps, and all these things. And then from the wind speed. Now, according to the type of application, you have to choose the, so one has to choose tip speed ratio lambda. Let's say lambda depends on type of applications. For example, let's say if you are doing water pumping, windmill, then you need greater torque needed. So your lambda should be between 1 to 3. For, let's say, electric power generation, you can use lambda between 4 to 10. Okay. So if you have higher speed machine that use less material in the blades and have smaller gearboxes, but require more sophisticated airfoil. So what you can say, higher speed machines use less material in the blades and have smaller gearboxes but require more sophisticated airfoils. Okay. Now you need to choose number of blades, which is B. So if fewer than 3 blades are selected, then there are a number of structural dynamics problems that must be considered in hub design. So one possible solution could be using tethered hub. So typically 3 blade is considered, and if it is something less than 3 blade, then one needs, now one has to select airfoil. So if your lambda is less than 3, then carb plates can be used. If lambda greater than 3, use more aerodynamic shape. Okay. What you can do now, you can, so that was our basic rotor parameter. Now what we'll do, we can define the blade shape. Okay. So here we can obtain and examine the empirical curves for the aerodynamics property of the airfoil at each section. So essentially what we need, you need this airfoil curves, that means CL versus alpha, CD versus alpha, and then we need to choose design condition, that means CL design and CD design, such that CD design by CL design is minimum at each blade section. So this is something very uh, uh, unique, because one has to use these empirical curves of the aerodynamic properties of the airfoil at each section. So these are so essentially one has to use this for at each section. So that means there are different airfoils can be. Then we can divide the blade into number of elements and use the optimum rotor theory to estimate the shape of the each blade. So we can divide the blade into n elements and estimate shape of ith blade using optimum rotor theory. Okay, so that means we can have lambda ri equals to lambda ri by r, that is 1. Then we have phi 2/3 1 by lambda ri. 2, we have ci 8 pi ri cl design I 1 minus cos phi 3. Then we have theta ti, theta pi minus theta p0, which is 64. So this is the twist angle. And then pi theta pi plus alpha design I. So that's what you get here. Alpha is the angle of attack. This is pitch angle. So this is initial pitch angle, or I mean pitch angle at the up. So you get all these at shape parameters of the blade for that. Now, using this optimum blade shape as an initial guide, we can select a blade shape that promises to be good approximation. And also for each of fabrication, some linear variation of the chord, thickness, twist might be chosen. For example, so what we can say that now using the optimum blade initial data, we can select blade shape that promises to be a good approximation. So for ease of fabrication, some linear variations of chord, thickness, twist, chosen. For example, let's say if A1, B1, A2 are coefficient for chosen chord and twist distribution coefficients, then Ci is A1 Ri plus B1, theta I is A2 R minus Ri, this is B1. 66, 67. So if A1, B1, A2 are the coefficients for a chosen chord and twist, then the chord and twist can be expressed like that. So these are some example that how this linear variation could be. Now the final part to that would be calculate rotor performance and modify design accordingly. So here, I mean, what one has to do, I mean, now we can use the method that we have already talked about, either method one or method two, and then consider, um, I mean, calculate the performance, and then accordingly you can modify the design of blade. Okay. So what we can, so our method one, again, you solve for CL and an alpha. So we can find the actual angle of attack and lift coefficient for the center of each element by using the equations and the empirical curve. So like CLI equals to 4 Fi sin phi, then we have cos phi minus lambda Ri sin phi. You have sigma prime I sin phi plus lambda Ri cos phi. So that may what we are trying to solve for CL and alpha, but actual angle of attack and lift coefficient for center of each element. So here sigma prime I is BCI by 2 pi Ri. And we have phi equals to alpha P, P0. So which includes the initial pitch angle, twist angle and all this. And our Fi is 2 by pi cos inverse exponential b by 2 1 minus Ri by r. Then we have r by r sin phi. Now the lift coefficient and angle of attack can be found by iteration or graphically. Typically the graphs could be like one can have variation of alpha, which is CL, it goes like that, and some curve is there. So this is alpha I, this is CLI. So now CL and alpha either found iteratively or graphically from the CL versus alpha curve. But obviously, if someone wants to do iteratively, this requires some initial estimate or guess. So guess of tip loss factor. So to find a starting Fi, so to find starting Fi, so we can, to find a starting Fi, we can start with an estimate for angle of relative wind by Pi 1 2 by 3 tan inverse 1 by lambda Ri. And then in subsequent iterations, we can find Fi using phi ij plus 1 Pi plus alpha ij. So here is the number of iterations. So it basically goes in iterative. Usually only a few iterations are needed to get a converged solution. And then finally, we calculate the axial induction factor, which is AI by 1 plus 4 sine square phi by sigma I CLI. Okay. So this is the axial induction factor. Then you have to need to check if AI greater than 0.4 or not. If it is greater than 0.4, then actually we cannot use or use this design consideration. We have to actually use the method 2 that we have discussed earlier, but we will do that discussion here as well. So essentially this method, what we do, we try to solve the CL and alpha. And the initial angle of attack, that CLI, you get calculated using equation 68, and where solidarity is also you calculate, and then calculate the phi, fi, and all these things. But then you try to get the CL and alpha by iterative process or graphical process like this, where you have the plots and then each sections you get some graphical method. But iterative method is slightly more robust in that set. You start with some initial guess factor of Fi and then calculate the phi I. And once you converge to phi I, then you get the axial induction factor. So that's how you find the CL and alpha and all these things. But once you find out EI, you check whether this is valid or not and then move to the other, which we'll talk in the next session.